All right, hello and welcome to our slightly modified office hours. Let me know when you have any questions. We'll get into it. Okay, there we go. Sorry about that. I was having some technical difficulties where my computer started, but everything has been troubleshot at this point. So, Margot, I'm going to answer your question first, and then Miriam, I will get to your question second. So for balancing, so for determining the number of electrons exchanged in a redox reaction, let's go ahead and look at the reaction between silver cation and magnesium metal. And this reaction will produce magnesium cation and silver metal. Now, the way you determine the number of electrons exchanged in this reaction is you need to compare so you need to balance this using the half reaction method. And you don't actually have to finish the balancing process, but you need to follow that protocol up until you're balancing electrons. And once you've balanced your electrons, then you'll know the electrons that have been exchanged. So first step, we need to break this into two half reactions, one where silver cation is becoming silver metal, and the other where magnesium metal is becoming magnesium cation. right, so what we need to do first is balance the charge. We already have the atoms balanced, right? For each half reaction, there's 1 silver and 1 silver on both reactants and product sides, same with magnesium. So if you look at your charges, for the silver half reaction, there's a charge of +1 on the reactant side and a charge of 0 on the product side. Now, when you're balancing charges, the only thing you can use to balance them the only thing you can use is electrons. You can add electrons to either side. So we are going to add 1 electron to our reactant side so that we get -1 + 1, giving us a total charge of 0. Same story with magnesium. We're going to look at our charges. We have a 0 on the reactant side and a +2 on the product side. We're going to add electrons to the product side of this half reaction so that we have the same charge on both sides. Now we have a +2 minus the 2 negatives from our electrons, giving us a total charge of 0 on both sides. All right, so let's go ahead and take a look. So now that we've balanced our charges, now we need to balance our electrons. And what that means is we know that the number of electrons consumed by one half reaction must be equal to the number of electrons produced by the other half reaction. But here, as written, the silver half reaction is consuming 1 electron, the magnesium half reaction is producing 2. So we need to multiply our silver half reaction by 2. This would give us, let's keep our colors consistent here. 2 electrons react with 2 silver cations to produce 2 silver atoms. All right, now our electrons are balanced because we are consuming the same number of electrons that we are producing. And that number is 2, and that is the answer that this problem is looking for. 2 electrons are exchanged in this redox reaction. All right. Okay, so Miriam, you want me to check in on a couple problems from exercise 8. Give me 1 second while I log in. Margot, you are so totally welcome. Sorry for the technical difficulties at the beginning of the stream. My tablet was not functioning, so I wasn't able to draw for a little bit there. I so appreciate your kindness. It can be in short supply these days. All right, let's see. Assignments. I don't know if this has been happening for you guys, but Canvas has been super laggy. For me, like it's just been in general like bad at loading things. All right, let's see. All right, so because this assignment is still live, I can't do the problems with the actual numbers, but I can definitely change the numbers and show you how to solve these problems. Yeah, I don't know like why. Like sometimes I'll like click on an assignment and like have to refresh the page like 3 times or have to like navigate all the way into it again. It's like it's been sucking hard. I actually had Canvas crash, like just go completely down at a different college that I'm teaching at, not at FLC, but another one's Canvas just went black for an entire day. And of course, it was the day that an assignment was due, so so it induced a lot of anxiety. All right, so let's see. So let's do exercise 8, number 6. All right, so let's see. So the original problem is 6 grams of acetic acid are dissolved in 200 grams of benzene. What is the resulting freezing point depression? Okay, so I'm going to change this around. Again, just altering the numbers a little bit. Okay, so I'm gonna do 0.4000 grams of acetic acid. Dissolved in, I'm gonna do 350 grams of benzene. Okay, so let's see. And then we're being asked here to find the freezing point depression. In other words, this is the amount the freezing point changes. All right, so we're asked to find the amount the freezing point changes. All right, so there is an equation that we need to be dealing with here, and that is the change in freezing point. The freezing point depression is equal to negative I times the molality times the freezing point depression constant. All right. Now, because we're dealing with a covalent compound, I is just equal to 1. The freezing point depression constant is something we need to look up. We need to look up the freezing point depression constant for benzene, which is, let's see, benzene has a KF of 5.12, and the units here are degrees Celsius over moles per kilogram. Some weird units, but these are actually the units for molality right here. So the molality units end up canceling. We're left with degrees Celsius, which is good. And now we need to find the molality of the solution. Now, molality is a concentration unit that is equal to the moles of solute divided by the kilograms of solvent. All right, and the kilograms of solvent are right here, or almost right here, right? We need to convert this to kilograms. And then we get the moles of solute from, again, we got to do a unit conversion to pop that into moles. So this is going to take a couple unit conversions, but we are up to the challenge. So first off, let's take 350.0 grams of benzene and convert it to kilograms. Grams cancel. And this will come out to be 0.3500 kilograms. Next, let's get moles of acetic acid. So we have grams of acetic acid here. We need to convert our mass to moles. And to do this, we'll need to calculate a molecular weight. Acetic acid has carbon, hydrogen, and oxygen. And we have 2 carbon, 4 hydrogen, and 2 oxygen. So busting out my calculator, not my stopwatch. We have 2.01 times 2, 1.008 times 4, plus 32. So this comes out to be 60.052. got 1 mole. Grams cancel. And again, I'm busting out my calculator because I can't do this in my head. So 0.4 divided by 60.052 comes out to be 0.00666. Well, isn't that fun? 0.89 moles of acetic acid. We can only keep 1, 2, 3, 4 sig figs. 1, 2, 3, 4. I'm going to wait, of course, to round at the end, because now we can calculate our molality. So molality is equal to moles of solute, 0.00666.089 moles over 0.3500 kilograms. So our molality comes out to be 0.0190311. This is moles per kilogram. Again, our numerator has 4 sig figs. Our denominator has 4 sig figs. Our answer must only have 4 sig figs. But I'm waiting to round till the end. But I'm putting these lines here to remind myself that that's how many sig figs I have in play. All right, now we are actually ready to calculate the change in freezing points. It's equal to negative I, which is 1. Oh, well, I have it written up there. 1 times our molality, which is 0.0190311. This is moles per kilogram. Again, this has 4 sig figs. Times 5.12 degrees Celsius over mole per kilogram. You'll notice that moles per kilogram cancel, leaving us with degrees Celsius, which is excellent. So we multiply these two, or 3, I guess, because we are multiplying by 1, numbers together. And our change in freezing points will be equal to negative 0.097439336. We can actually only keep 3 sig figs because of the freezing point depression constant is a measured quantity, so that'll limit the sig figs in this problem. 3 rounds down, so our freezing point depression is 0.0974 degrees Celsius. All right, now one thing to keep in mind is this is the way it's formulated if you were then to calculate the freezing points. But technically, to answer the question, find the freezing point depression. Oops. You are, oh, hang on. There we go. You are only going to, because of the way the problem's worded, you're only going to be presented with positive answers. So if these were the numbers you were given, it would be 0.0974 degrees Celsius is how you would answer that business. All right, Ashna, Miriam asked for problem 6 and 7, so I'm gonna bust out problem 7 here, and then I'll answer your question. So stay on the line. All right, this is exercise 8. Oh, sorry. Exercise 8, number 7. How many grams of diethyl ether were dissolved? So here. Of diethyl ether, which is C4H10O. And again, I'm going to change the numbers. Were dissolved in 300.0 grams of benzene. If the resulting solution has a boiling point elevation of 0.64 degrees Celsius. All right, so one of the things you'll notice about this problem, so this one's kind of next level, definitely a challenging problem. And the way you want to go about solving this, so notice what you're asked to find. This is grams of solute. All right, it's a liquid solute, but it's a solute nonetheless. You're being asked to find grams of solute. We saw earlier that the equation of molality was equal to moles of solute over kilograms of solvent. So moles of solute doesn't equal grams of solute, but given one, we can find the other, especially since we know the molecular weight. So you want to be thinking, as we do this problem, molality, finding the molality is how you find the moles of solute. Moles of solute are how you find grams. Another thing you'll notice, kilograms of solute, you're given a mass of solvent, right? You know that you have 300 grams of benzene. So that is how you find the denominator of this. So as we move through this problem, you need to be thinking, okay, molality is how I find this. Now, we were told that it has a boiling point elevation of 0.64 degrees. That's a little too similar in color. Boiling point elevation of 0.64 degrees. That's a change in boiling points. So we've been given this. We know change in boiling point is equal to I times molality, which is what we need to find to get to our moles of solute. So this is really what we're after. Times our change in boiling point, our boiling point elevation constant, which for benzene we can look up. The boiling point elevation constant for benzene is, 2.53 degrees Celsius over moles kilogram. So we got this. I, because this is a covalent compound, is equal to 1. Which means we can use this equation to find molality. Once we find molality, we can find moles of solute, and then we're there. So, going off that equation, change in boiling points is equal to I times molality times Kb. We divide both sides of this equation by I and Kb. So molality will be equal to our change in boiling points over I times Kb. We have all of these numbers. Our change in boiling point is 0.64 degrees Celsius. I is 1. Kb is 2.53. This is degrees C over moles per kilogram. Degrees Celsius cancels. So we can find our molality by dividing 0.64 by 2.53. So our molality then is equal to 0.25296. We can only keep 2 sig figs, but I'm going to leave all of the numbers here because you wait to round till the very end, and our units are moles per kilogram. All right, now we know our molality. And we can use that molality to find our moles, because molality is equal to moles over kilograms. To find the moles of solute, we need to multiply both sides of this equation by our mass of solvent in kilograms. So our moles of solute will be equal to the kilograms of solvent times molality. Now, we don't actually know explicitly what our kilograms are yet, mostly because we have to do a unit conversion. We have our mass of solvent in grams. We need to convert this to kilograms. So this comes out to be 0.3000 kilograms. So 0.3000 kilograms times our molality, which is 0.25296. This is moles per kilogram. Again, we only have 2 sig figs here, and you'll notice that kilograms cancel, which is good because we're just after moles. So let's crunch these numbers, and we have 0.075889 moles of our solute, which has a chemical formula C4H10O, and we have 2 sig figs in this number. Now, something you have to be aware of. So we need to take this number and convert it to grams. To do that, we need to calculate a molecular weight for diethyl ether. So diethyl ether has carbon, hydrogen, and oxygen. And we have 4 carbons, 10 hydrogens, and 1 oxygen. So 1.008 times 10 plus, 12.01 times 4 plus 16. So this comes out to be 74.12. So we can now take our moles, which is not 0.75, 0.075, 889. Actually, I'm going to need this whole row. C4H10. Oh. And there's 74.12 grams. What am I doing? I just set up this thing wrong, and here's how you can tell. Moles doesn't cancel grams. We're trying to find grams, right? Let's try this again. So we're going to put moles in our denominator. So we're going to multiply 74.12 times 0.075889. My calculator is telling me the answer is 5.62489. But we got 2 sig figs here. 2 rounds down. So we got 5 grams of diethyl ether was dissolved in 300 grams of benzene. That resulted in the boiling point elevation of 0.64 degrees. All right, Mariam, so that is the answer to both of your questions. Ashna, you have been waiting patiently, and I think we have time for one last problem. So let's dive in. Thanks for hanging around and being so dang cool. All right, so let's see. So this is an example from exam 1. Hydrogen. Okay, so here, let's see. So hydrogen represents 10.06% of the mass of a molecule whose chemical formula is CzH4. And so we're being asked to find Z. All right, now to find Z, and we're also given the atomic mass of carbon and hydrogen to use. So to do this, we need to know the mass percent of carbon, which we can find because we know there's 100% of the mass in the molecule. We can subtract the mass of hydrogen, 89.94%. So we know this molecule is 89.94% carbon. All right, now, the mindset you want to get into when you're solving this problem is one of finding the empirical formula, because that's the type of problem that this specific one is based off of. We know that hydrogen is 10% of this molecule, and carbon is, or 10.06% of this molecule, and carbon is 89.94. So let's, for a moment, assume that we have 100 grams. All right. If we had 100 grams of this compound, whatever it is, we'd have 10.06 grams of hydrogen and 89.94 grams of carbon. Now, here's why this is useful. The ratio between the number of hydrogens in this formula and the number of oxygens, which I'm trying to figure out, this is a mole to mole ratio. And because we know the percentages of each, the mass percentage of each, we can convert these masses to moles, and that'll give us the mole to mole ratio. So we can use the ratio we derive from our 10.6 grams of hydrogen and our 89.94 grams of carbon, and use it to figure out what number Z is. All right, so let's take hydrogen and convert this mass to moles. Let's take our mass of carbon, convert it to moles, and crunch some numbers here. So 10.06 divided by 1.008 comes out to be 9.980 moles of hydrogen, and then we go 89.94 divided by 12.01. Whoops. 89.94 divided by 12.01. There we go. So this comes out to be 7.489. We don't actually have to be that careful with sig figs here. We just need to not like round them to one digit, but our answer is going to be an integer. So this is our mole to mole ratio of hydrogen to carbon. It's hard to know what it is just looking at it. So let's simplify things and divide both of these by the smaller of the two. Let's divide both of them by 7.489. When you divide that, we get, for carbon, we get 1 mole, right? Because 7.489 divided by itself is exactly that. Now let's take hydrogen and divide it by 7.489. This comes out to be 1.33 moles of hydrogen. In other words, this is 1 1/3, or 4/3, right? Because that's how that decimal converts to a fraction. It's 1 1/3, or as an improper fraction, it's 4/3. Now we can use this. Here's how. Got to make a little bit of space here. So we know from this formula, if we're going to go carbon on top, hydrogen on the bottom. From our formula, it's Z to 4, right? That comes from our formula. But we also know, coming from our percentages, we just calculated that the ratio of carbon to hydrogen is 1 over 1.33, right? That's the ratio we just calculated. And these two are equal. They're the same ratio. So now we can use algebra to solve for Z. We can solve for Z by multiplying both sides of this equation by 4. So if you take 4 divided by 1.33, this comes out to be 3.007. So that means Z equals 3. So this compound would have a chemical formula C3H4. You are so totally welcome, dude. Awesome. Alrighty, I gotta bounce because I actually have a second office hour right after this one. But thanks to everybody who showed up. It was a awesome batch of questions. Margot, you are so totally welcome. Have an awesome day. Yeah, it was a very mix of questions. It's a good time. All right, I'll catch you guys all on the